So this next video will be rates of change in linear, quadratic, and cubic functions. And we've been talking about rate of change in tandem, but this is the first time we're actually digging into it analytically using numbers to see what's happening beneath the surface as to why a function might be linear, quadratic, cubic, etc. So the first thing that we need to get comfortable with is we are going to be using common differences, and that is going to be basically the value between two of the numbers listed. So if I go from 1 to 2, that common difference, or not common difference, but that difference will be 1. And I want to compare the differences and see where the commonalities might lie. Something else we need to look at is the notation here. So a sub n, you can think of that as f of x, right? It serves that purpose. We will plug in a value and then we will get an output. Now, the values that we plug in for this, n is going to be only integers greater than 0. So 1, 2, 3, 4, etc. So if we were to plot this or graph it, it would not be a continuous curve, it would just be dots on the graph, okay? So n is going to be an integer. And remember, z is used for integers because in German, the word for integers begins with a z. It's like Zelan, or I'm definitely mispronouncing that, but that's why we use z for integers, okay? But these integers, they have to be greater than 0. So I'm going to say such that n is going to be an integer that is greater than 0. So integer greater than 0. You don't have to write these. This is definitely beyond the scope of this lesson, but if you plan to study mathematics later, you'll see this terminology. So you can either write it down or just completely forget about it, okay? Greater than 0. Now going forward into the actual context of the course, we will look at n to the power of 1, which is linear, n to the power of 2, which is quadratic, and then n to the power of 3, which is cubic, okay? So if we look at linear first, if I plug in my first integer, which is 1, 1 to the power of 1 is equal to 1, okay? The next integer is 2. 2 to the power of 1 is 2. And if I keep going, 3 to the power of 1 is 3. We're just going up by plus 1 each time, okay? And then what we're looking at is the differences between these outputs that we're getting. And we're just putting them in a list, okay? So from here, from 2 to 3, that's a difference of 1. 3 to 4 is a difference of 1. 4 to 5, 1. 5 to 6, 1. 6 to 7, 1, okay? And this continues on to infinity. So because the first common difference is the same, and that's redundant because it's already a common difference, which means it has to be the same, but just so you guys can see what we're looking at, the common difference is the same, the slope is constant. Therefore, linear. And the 3 dots mean therefore. So because we only had to look at the first differences and they were common, that means it's the first common difference, all right? So another star here is we use the first common difference. And then hopefully without even seeing us do the quadratic, you can be like, okay, well, if this is n to the power of 2 and it's quadratic, start to already look for a pattern. That's a pattern. That's all math is. It's just recognizing the pattern and applying that pattern to other forms of what we're looking for, okay? So now we have a sub n, and now we have n squared. So if we plug in positive integers, we get 1 to the power of 2, which is 1, 2 to the power of 2, which is 4, that's that second term, 3 to the power of 2 is 9, and then so on and so forth, okay? And this goes on to infinity. So now looking at the differences, from 1 to 4, that's a difference of 3. 4 to 9 is 5. And then 9 to 16, we have 7. And then you should be able to see a pattern already, all right, without having to do, okay, 25 minus 16 and then 36 minus 25. I can see that we're increasing by odd values, okay? So we'll go 3, 5, 7, 9, 11, and then 13. Now, these are not common, all right? So we're going to have to try again by going to the second differences, which means we apply this same difference, but to the first difference, okay? So from 3 to 5, that's a difference of 2. 5 to 7, 2. 7 to 9, 2. 2 and 2. So now we found our common difference, okay? So because the second common difference is the same, the rate of change is constant. But though the rate of change is constant, you can see that it's positive, all right? So it's a positive constant, which means if the rate of change is a positive constant, that means the rate of change itself is increasing. So because let me see, I think I'm missing a word here. Yes, I am. So how can I fix this? So the change in the rate of change is constant. That's what I was missing. Because if the rate of change is just constant, that's just positive. That's linear. But the change in the rate of change is constant, which is positive. So we talked about this a couple lessons ago about concavity, how a curve is concave up when the rate of change is increasing. So now with this one, we're talking about the rate of the rate of change, or the change in the rate of change, and how it's constant, which means therefore the rate of change is increasing. And because that rate of change is increasing, therefore it is concave up. So we have a quadratic, therefore quadratic. Now, obviously not every concave up curve is going to be quadratic or parabolic, but in this case, because we use the common differences, we know that this is going to be a quadratic. Okay, so I know that's a little confusing. We're looking at the change in the rate of change. Basically, we're talking about how it's increasing, or how the rate of change is increasing or decreasing. All right, so this one here is, we use the second common difference. Now let's look at cubic. We're not going to dig too deep into this. I just wanted to show you this one so you can see that the pattern does continue to infinite degrees. So from 1 to 8, that's going to be 7. 8 to 27, that's 19. 64 minus 27, get 37. 125 to 64, 61. And then 216, 125, 91. And then from here we have 127. All right, so we don't have a common difference, so let's go down another level. 7 to 19 is 12. And then we have 18, 24, 30, and 36. So now, hopefully you've noticed the pattern. Because it's a degree 3, that means we're going to have to go down 3 differences. 12 to 18 is 6, 18 to 24 is 6, 24 to 30 is 6, 30 to 36 is 6. Okay, so that means for this one, we use the third common difference. Okay. All right. However, the focus will be these two, first common difference and the second common difference. So on this page, next is going to be talking about basically how we will see a linear function. So for any linear function, the average rate of change over any length input value interval is constant, okay? Is constant. So basically the slope from A to B equals the slope from B to C. So if I was to plot this, we could say this is A to B and then B to C. And notice that it says any length input value interval, but when we talk about these in the context of this course, these intervals will need to be equal in order for you to observe whether the slope is constant or it's quadratic, or it's creating a quadratic function. So note, we often think of this as the slope of the line. Well, I already said that, so. Okay, so let's see how this works. So the table above gives selected values of the function f of x. Explain why f of x is not a linear function. So if we look over here, just a quick note, to analyze, we do what we did on the previous page. So do what was done on the previous page. All right, however, we need, this is an important term, equal length input values. Equal length input value intervals. Okay, equal length input value intervals. So the first question is check the left. Are these input values spaced out equally? From 1 to 2 we have 1, from 2 to 4 we have 2, from 4 to 8 we have 4. If the answer is no, you're going to have to use the average rate of change. Now, if this was spaced out equally, 1, 1, 1, we could just go ahead and do what we did on the previous page and look at the difference between the outputs. But if you do not have equal length input value intervals, then you're going to have to use your average rate of change, okay? So on the interval from 1 to 2, think of this as A to B up top. From 1 to 2, we have the average rate of change is going to be 7 minus 4 divided by 2 minus 1, which gives us 3. Okay, so now let's check the next interval. On 2 to 4, the average rate of change is going to be 10 minus 7 divided by 4 minus 2. So we end up with 3 over 2. Now, in order for this to be linear, the average rate of change has to be constant. 3 does not equal 3 over 2. All right, therefore, this table does not represent a linear function. Okay, so f of x is not linear because I'm going to use the abbreviation for because, B/C, the average rate of change over any length input value intervals is not constant. So for constant, it would be any length input value interval, okay? Because you should be able to do a sliding scale, like whether my interval is here to here or here to here, it should have the same slope, the same average rate of change because it's a linear function, okay? But this one does not. Number 17, consider the quadratic function g of x equals x squared. Complete the table of values for g of x over the consecutive equal length input value intervals below. So this is important, consecutive equal length input values. This means that the input values will be spaced out consistently, Okay, so from -3 to -1, plus 2. -1 to 1, plus 2. 1 to 3, plus 2. 3 to 5, plus 2. Okay, so that's referring to the input values. Then complete the table for the average rates of change of g of x for each consecutive interval of equal length input values. Okay, so now we're switching from consecutive equal length input value intervals to consecutive intervals, because now the inputs aren't just a value, it's going to be an interval. Okay. All right, so let's fill in the table first. So when we plug in -3 into x squared, we get +9. Plug in -1, we get 1. Plug in 1, we get 1. Plug in 3, we get 9. Plug in 5, we get 25. All right, so now from here, the directions ask us to just complete the table. So from -3 to -1, we have an interval, so we're going to have to use average rate of change again, okay? So from -3 to -1, we're using these 2 points. So we'll have 1 minus 9 divided by -1 minus 3, which will just be plus 3. So we end up with -8 divided by 2, which is equal to -4. So we'll plug in -4 into that first box. All right, next we'll switch to pink. So now we're going to take the average rate of change between these 2 points. It'll be 1 minus 1 divided by 1 plus 1, which is going to be 0/2, which is equal to 0. So we'll go ahead and plug that in. The next interval is going to be these 2. So we'll have 9 minus 1 divided by 3 minus 1, which is equal to 8/2, which equals +4. And the last pair of points, we'll have 25 minus 9 divided by 5 minus 3, which is equal to, that'll be 16/2, which is equal to 8. All right, so what we just took care of over here, this is the first common difference. First common difference. I'm just going to write first common diff. So we can figure out the first common difference even if the intervals are not spaced out by 1 for the inputs, okay? So whenever you find the rate of change of a function, that is the first common difference. That is what these numbers represent. Now we can tell it's not linear because they're all not the same value, but we knew that from the start because it's quadratic, which means we will find a second common difference. So if we look at the second common difference, I'm going to look at -4 to 0, that is +4, from 4 to 4, 0 to 4, +4, from 4 to 8, +4. So we just found our common difference, but this is the second common difference. Okay. Now, this was consecutive equal length input values. So if we were to just use the y values, we would get, what would it be? It would be 1 minus 9, which is -8, 1 minus 1, which is 0, 9 minus 1, which is 8, 25 minus 9, which is 16. So if we look at this, we would have +8, +8, +8. So we would still have a common second difference, all right? And this works because we had consecutive equal length input values. So we could have just went straight to this instead of using the average rate of change. But that's only because the x values were spaced out consistently, okay? All right, what do you notice about the average rate of change of g of x over consecutive equal length input intervals? Okay, so it's kind of just what I talked about, the average rate of change of g of x. So we can go ahead and write this. The average rate of change of g of x over, and I'm just borrowing this from the problem itself, consecutive equal length input value input values is increasing. At a constant rate. So when I say the consecutive equal length input values, they are increasing, I'm looking at this 4, plus 4, plus 4, plus 4. But as it increases, it's constant. It's always plus 4, okay? Constant rate of 4. Therefore, the rates of change of g of x are given by, so when I say the rate of change is given, or the rate of change of g of x is given, I'm focusing on these. So now I'm talking about, I'm in the realm of the rate of change. I'm not talking about g of x itself anymore. I'm specifically talking about these values. So the rate of change of g of x are given by a linear function. So I'm going to zoom back up. So I'm talking about this second line. The rates of change are given by a linear function. Okay, so write that down. The rates of change are given by a linear function. So because the second common difference is constant, that means the rates of change are given by this constant rate, which is represented by a linear function. All right, this is the last part of this video. So selected values of various functions are given in the tables below. For each table, determine if the function could be linear, quadratic, or neither. Okay, so real quick, if the inputs are not consecutive, you need to use a difference quotient. AKA, that's going to be your average rate of change, okay? Difference quotient. So y2 minus y1 over x2 minus x1. So you're taking the quotient of differences. Okay, so let's zoom in on A. So if we look at this, if we look at the x values, we have plus 1, plus 1, plus 1. Okay, so we're good. We can just look at the outputs and see what's happening there. So from 0 to 1, I have plus 1. 1 to 4, I have 3. 4 to 9, I have 5. So this is my first difference. Okay, so we know this is not linear because the first difference is not constant. Okay, so now let's try again. So we have plus 2, plus 2. This is our second difference. And we have a second common difference because they are both the same. So because we have a second common difference, this is going to be quadratic. And I'm going to use the abbreviation BC for because the average rate of change forms a linear pattern. That's the same as represented by a linear function, or AKA the rate of change is constant. Sorry, not the rate of change is constant because that would be a linear function. The rate of the rate of change is constant. And it's positive, which means the rate of change is increasing. So ROC is increasing. So all of this means the same thing, okay? All right, if we look at B, if you look at the inputs, they are not consecutive. So we have plus 1, plus 3, and then plus 5. So for this particular example, we will have to use a difference quotient, aka the average rate of change. So if I look at these two, I'm going to have 1 minus 0 divided by 2 minus 1, which is going to be 1. For these two coordinates, I have 4 minus 1 divided by 5 minus 2. That's going to give us what is that? 3 over 3, so we get 1 again. And this last pair, we have 9 minus 4 divided by 10 minus 5. That's 5 over 5, which is 1. Okay, so this is our first common difference, and it's constant, okay? So that means this is linear because the average rate of change is constant. Cross your fingers you get this one. It's pretty straightforward. All right, the last one, we have 2, 2 again, and 2. Okay. So 2, 1, 0. 2, 1. I'm trying to remember this one. We go up by 2, we go up by 1, we go up to 0, and then we go up by 1 and 1. Okay, so I did this one in my notes. I did average rate of change for some reason. Oh, because I said consecutive. Okay, so it would need to be 1, 2, 3, 4, 5, or so on and so forth. However, this one does work because it's equal length input value intervals. It's 2, 2, 2. So let's play around and see if it works. So from -1 to +1, I go up by 2. From 1 to 2, I go up by 1. From 2 to 2, I go up by 0. Okay. So this is my first common difference. It's not common. It's just my first difference. It's not common. Okay. Now to get from 2 to 1, I use -1. To get from 1 to 0, I go -1. This is our second, and it is common because they are both the same. So again, just like A, we have another quadratic because the average rate of change forms a linear pattern, which is the -1s we're looking at. Okay. If you were to use the average rate of change, you would get use your difference quotient, you would get 1, 1/2, and 0. So that would be 1/2. That'd be -1/2. And then this would also be -1/2. So you would still get a quadratic, okay? So because this is consistent, 2, 2, 2, we can just focus on the outputs and get the same answer as if we did average rate of change. All right, hope that helps. I know that was long, but it's important that you understand how these common differences work.